It was still better than the chapter P test, so pass that down to Yasmin. Okay. So we're going to talk about what we call concavity and the second derivative. So we've learned stuff about the first derivative. We know we can get increasing and decreasing off the first derivative. And we know we can get velocity off the first derivative. That's right. Well, when we talk second derivative, we know we get acceleration from that. We also get what we call concavity from that. Concavity is whether the curve is going is up like a cup or down like a frown, right? All right, so it's up like a cup or down like a frown. All right, make sure you're writing your essential question because we're going to talk about determining the concavity of a function. I've got about 4 or 5 definitions and then about 4 examples today. I realize why this is so easy for you. I was going through the math analysis lesson for today, and I'm like, oh, relative max and min and increasing and decreasing. No wonder calculus is doing so well right now. Only we're just now starting chapter 1 in math analysis. So the way the curriculum was rewritten is just all over the place. We started with quadratics this year. So I'm not teaching them how to do graph a line at all, so they just got to know that. Yeah. They should at that point, right? All right, we ready? Yeah. Okay, here we go. Maybe. Get this going. All right, so the definition of concavity is that let f be a differentiable on an open interval I. The graph is concave down on I if f, the derivative is increasing. Okay, so this is weird. So I'd write this, concave up if f prime is increasing. So not your original graph. If your derivative graph is increasing, your function will be concave up. Okay? If on an interval, and concave down if the derivative is decreasing on the interval. And so here's the deal. They could give you the first derivative, they could give you the information for the second derivative, or they could give you the information for the original. And you have to be able to manipulate that information and get back and forth to all the concavity, get back and forth to all the increasing, get back and forth to all the maxes and mins. Okay? So we're going to practice that a lot. Okay? In fact, you'll probably be practicing a lot on Tuesday when Miss Salmon will be here for me. So, yes. Yes, I won't be in class Tuesday, so. Yeah, I have an all-day thing that I've got to do. So, okay, we good with that? So, and it shows you concave up like a cup, concave down like a frown, right? Okay, so the test for concavity. So I'd write down test for concavity, and I would write down if the second derivative is positive, we are concave up. If the second derivative is negative, so I'd write this line down, and I'd probably write my little negative sign, right? Then we are concave down. And that's really all there is to it. You go to your second derivative. If you're positive, you're concave up. If you're negative, you're concave down. Okay. The interval issue works the same way it does with the first derivative. Okay, so this really isn't, it's new, but it's not new. You understand the concept, hopefully, already. Okay, so let's look at, you ready? No? Okay. Well, it's because Aaron probably didn't write it down. Did you? Wow. Okay. Okay. All right, here comes the next one. Go ahead and write that example down. All right, so we are supposed to determine the open intervals on which the graph is concave up or concave down. So what derivative do we get concavity from? Second derivative. So I'm going to take that all the way to the second derivative. So h prime of x equals, what's the first derivative? Good. What's my second derivative? 20x cubed. How do you think I get my critical point? Set it to 0. Now this gives you the critical point for concavity, okay, which we're going to give a name to here in a minute. You might already know what it is, but okay. Well, so I get 0, right? Cubed root of 0 is 0, like that. So I'm going to use my sign chart again for my second derivative. I'm going to label it as my second derivative sign chart. You know how on the sign charts we've been getting that plus, minus, minus, plus thing going on? And I said there's something else going on there. Well, it's probably a concavity, okay? So not always, but it could be a concavity kind of thing, okay? Do I want to know? Okay, so I'm going to plug into this second derivative here, all right? And I'm going to plug in what, -1? What's -1 cubed? So it's going to stay negative, right? So that's negative there. All right, I'm going to plug in a positive 1. What's positive 1 cubed? 1 times 20 is? Positive. All right, so now we're going to talk about our intervals where it is concave up. Concave up like a cup. Look, if you abbreviate it, it even abbreviates to cup, doesn't it? That's pretty cool. All right, concave down like a frown. Okay. All right, so where is the, or we should probably say H is, right? H is if we're actually trying to write a sentence. So H is concave up where? 0 to infinity. Where is it concave down? Good. That was pretty easy, right? Okay. The next part of this is putting a name to what that is right there, okay? When we were talking before, we were talking about maximums and minimums. Well, there isn't a maximum or minimum at this point, okay? It just changes concavity. We call this point a point of inflection, which I know you've seen that before, okay? So, well, let's see, how would we define it? The concavity changes, so point of inflection of the graph of f if the concavity of f changes from up to down. That's good enough definition. You don't need to write all that extra words, okay? I'll give you a minute to write. If you need example graphs, there's a bunch of them there. All right, we ready? No? Okay. So this one again, it's another little bit more information about that point of inflection. So your point of inflection, if you have this point, okay, if the point is a point of inflection, then either the second derivative equals 0 or the second derivative does not exist. Meaning somehow it gets undefined somewhere, right? So if you have a point of inflection, either your second derivative is 0 or your second derivative does not exist. Those are our two options. All right, next example. Same instructions as the last example. We just added more to it now. We're going to find, oh, no, I guess they're different. We're going to find the points of inflection, okay? Did I go too fast? Yeah. Sorry. Just f double prime equals 0 or f double prime does not exist. You don't need to write every single word, remember. In college, they're not going to stop. In college, they might not even show you any examples. They'll just explain that. That's what Brenna's telling me right now. Brenna says that right now her calc class is all theory. They don't do hardly any examples in class. She's liking it. She's getting it because she took the 2 years here, but she says it's a lot different and a lot faster. All right. So we are going to find the points of inflection and discuss the concavity of the graph of the function. And it is possible to have more than one point of inflection. So the concavity, it could be really loopy, right? It could change a bunch. Okay, so what do I need to do if I'm going to find points of inflection or concavity? Find the second derivative. So my first derivative is? Good. My second derivative is? Minus 24x. Okay, what am I supposed to do with that to get a critical point for the second derivative? Set it equal to, remember, we used to get our critical points from the first derivative, and we still can. And some of the points that come up here might pop up in the first derivative. In fact, they should, okay? Because a point of inflection is still a critical point. All right, what should I do? 12x sounds good. So we're left with x minus what? 2. All right, good old zero product property, one of our favorites, right? So what is x equal to? 0. And 2 are our critical points. Now, they're technically points of inflection. I'm not going to actually state that they're points of inflection until I actually test it on my sign chart. Because if I come out with a plus plus or a minus minus, they're not a point of inflection. It was just some other critical point, okay? Or maybe an asymptote or something weird, okay? Likely they'll work out on most of them, but you never know, okay? But then once we find them, we're actually going to plug back in today and get the actual y values today. All right, so I know I've got 0 and 2. I know when I plug in, I'm going to plug into here because I'm testing the second derivative sign chart. So what is a good negative value for me to plug in? Negative 1. All right, so what is negative 1 squared? Positive 1, it's going to go 12, right? So I know I've got a positive 12. What's negative 24 and times negative 1? Positive. So am I going to come out positive or negative on this? Positive. Good. All right. I'm going to put in a 1. So I know that the first term is going to stay positive, right, because it's squared. What's negative 24 times 1? Negative. So 12 minus 24, is it going to be positive or negative? Negative. All right. 10, right? That's a good one. So what is 10 squared? 100 times 12 is? 1200 minus 240, positive or negative? Positive. All right. So do I have a pattern in my signs where I'm repeating? Yeah, so I know that I definitely have points of inflection. We'll talk about the concavity and then we'll go back and actually calculate the points, okay? So we would want to write that f is concave up like a cup on what intervals? Negative infinity, 0. And remember, you got to kind of ignore my little sub-ins, huh? That's why I don't draw a dash on them. And where else? 2 to infinity. F is concave, and I'm abbreviating. When it's a test, especially the actual AP test, you write out that word, okay? Concave down like a frown, where? 0 to 2. Okay, now we want to write the points of inflection. We know we've got 1 at 0 something, and we know we've got 1 at 2 something. Okay, so yes, we're going to have to plug it back in. But when I plug back in, I got to go to the actual original. So I'm plugging into the original. What do I get when I plug in 0? 0, good. What do I get when I plug in a 2? What's 2 to the 4th? 16 minus 4 times what, 8? What's 4 times 8? So it's going to be negative 16. And notice, you want to label that as points of inflection because look at how similar that looks to interval notation. It's identical, right? So the other way you will see this written, and this is the way it tends to pop up on the AP test, they will start writing points like that, okay, in function notation. So you know that it's a point. And you just know whatever's in the parentheses is the x, whatever's on the other side equals is the y. Yeah, go ahead. All right. Are we good with example 2? Yes. Okay. Let's keep going then. All right. Last little theorem that we've got to deal with today, it's called the second derivative test. Very rarely do I see this used, but it comes up in weird spots. I think there's 1 or 2 of the free response questions that I've seen that it comes up at random, kind of. In order to get through it, you only have information on a second derivative, so you've got to be able to use this. So when your second derivative is positive, you know that your actual function has a relative min, okay? When your second derivative is negative, your function has a max, okay? If it actually equals 0, the test fails. So you might want to underline that or write that. So if it equals 0, you can't use the second derivative test to figure it out. Okay, you ready? Now notice, it says that we're actually evaluating right at C this time. Okay, so we're going to actually plug the values in. This is a little bit different. Remember, it's a different test. Okay, so we're going to find all the relative extrema. We're going to use the second derivative test where applicable. Okay, so let's start by taking the first derivative. So what do we get for our first derivative? Plus 15x squared, good. Okay, let's go ahead and get our critical points off of that this time. So I'm getting my critical points next. So I set equal to 0, what do I do? I'm going to take out a negative 15x squared. What are we left with? Minus 1. Okay, so I do my good old zero product property thing. So x ends up equaling 0, and x ends up equaling plus or minus 1. Okay. Now, I'm supposed to be showing you how to use a second derivative test, so that's what I'm going to do. So let's take the second derivative of the function. I know where my critical points are. Okay, so I could use these points on the sign chart. So what's the second derivative of the function? Plus 30x. Okay, and I'm going to go ahead and get out my sign chart. So here's the difference. Okay. On the second derivative test, we don't test in between on the interval. We actually plug the actual number in. Okay, and I'm going to test for positive or negative. Okay, so when I plug the negative 1 in to this function here, I need to know if I get positive or negative. Okay, so what happens when I plug in a negative 1 into a cube? Does it go positive or negative? Negative times a negative is going to be, so I get positive 60, okay, and then 30 times negative 1 is, so is that going to be positive or negative on the negative 1? Positive. And notice I'm writing it right above my little mark because I actually plugged that number in. Okay, we'll go back and then analyze it here in a minute. What happens when I put the 0 in? It goes 0, which means the test fails. Most likely that's a point of inflection, right? When it's neither a max or a min, it's probably a point of inflection. All right, when I put in the 1, I get what? Negative 60 and positive 30, so is it positive or negative? Negative. Okay, now let's go back and look at that test. When you plug in the actual number to the second derivative test and I get a positive, what's going on? It has a relative min. If I get a negative, it has a relative max. Okay, so now let's go back and do that. Where do I have a relative min? -1. And we're actually gonna plug in the value. We'll get the point here in a minute. Where's my relative max? 1. And likely this 0, 0 is probably a point of inflection. Okay, so if I want to get that actual value, I want to get the y values for the actual coordinates, what do I need to do? Plug in where? To the original function. Okay, so -1 to the 5th power, is it going to be positive or negative? -1 times -3 is 3. Okay, the cubed, is it going to go positive or negative? Negative, and so times the positive 5 would be negative. What do we get? -2, good. All right, now we're going to plug in the positive 1, which means I just ignore the x's, right? So I get -3 plus 5, which is 2. So we have relative min at -1, -2. We have a relative max at 1, 2, and we have a point of inflection at 0, 0. Okay? All right, let's go one more. All right, we're going to use the same thing. We're going to use a second derivative test where applicable. So write same instructions, just write the example down. Okay, if I need to find the relative extreme at what test does it say we're going to? The second derivative test. So I got to get my first derivative to begin with. So f prime equals what? And then chain rule gets us a 1, right? Okay. All right. Let's go ahead and get my critical point off of that. So my critical point would be divide by 2. I get that. Probably didn't need the parentheses. So where's my critical point? X equals 5. So there's my critical point. All right. What do I have to do now? Second derivative off of this piece right here. Okay, that's just think about it. Couldn't I distribute that in? So it's really like saying -2x plus 10. What's the derivative of that? -2. So now let's try our sign chart. Okay, I know my critical point is 5. And I have to plug into here. No matter what I do to plug in that 5, I'm always going to be what? Negative. Think about that. We're talking, that's concavity too, isn't it? Isn't this an upside down parabola? Yeah, so shouldn't it always be concave down? Yep. So this will always be what? A max or a min? That's a max. So we're going to have a f has a relative max at, what's my 5? I got to plug back into my original. When I plug 5 minus 5 is what? So at 5, 0 is my relative max. So we're going to practice, yesterday or the rest of the week I let you get away with the x equals thing, right? Today let's practice plugging them back in to get the y value, because sometimes you need it, sometimes you don't. All right, that's it for today. I'm going to split this into 2 homeworks. Next week gets really weird with the day off on Monday, and then I'll give you a worksheet Tuesday, and then the rest of the week it's kind of hints and a test. Okay. Homework 66 for next Monday is technically going to be test corrections. This does not mean don't do 65 tonight. Okay, it means do them both. I'm just giving you double homework points. Okay. This is going to be your test corrections for the chapter 2.4 to 2.6 test. Okay. Bonus, you're getting it back like almost a week before you take the next one, right? I know, that like never happens. I know.